Okay, in our last video, we talked about lots of different applications of exponential growth, different growth models. Well, today we're going to focus on decay models. What are some things that we use exponential decay for? And to introduce this, I wanted to go back and look at this form of an equation that we looked at in our last video, but I just wanted to remind you of. This is telling me that the rate that my n function changes is equal to negative 0.062 times the function value of n. This is telling me that the rate of change is directly proportional to the function value. What does that mean about this equation? It's exponential. Okay, this is an exponential equation, and this is how the function or the rate of change relates to the function value. Well, notice that in this case, it's negative. That constant is negative. What does that tell you about how it relates? It relates in a negative relationship. If it relates in this negative relationship, what type of exponential function do I have? This tells me this is exponential decay. Right? I think we called this in our last video the growth rate. Well, if the growth rate is less than 0, I'm working with exponential decay. And so that's what we're going to focus on today. We're going to focus on exponential decay, where we see this in different examples. So exponential decay, a good example of this is carbon dating, if you've heard of that, in archaeology and things like that. Radioactive decay is modeled using exponential functions, okay? And with radioactive decay, you often hear this term half-life. Well, we're going to talk about that today, okay? Present value, if we turn to finances, present value is related to exponential decay, because present value is asking, okay, if I want a certain amount in the future, how much do I need to invest now? And it turns out you can calculate that using exponential decay functions. Also, if you have any sort of product or any sort of thing that depreciates in value, if it's losing value, a lot of times, like a car, right? A car depreciates in value. A lot of times you model that using an exponential function. Okay. Value depreciation. Cooling objects. Okay, if you pull a pie out of the oven and let it cool, that the temperature of that pie will follow an exponential model. And it's an exponential decay model because temperature is falling, it's decreasing. So we're going to look at a few of these today and see how we model them using exponential functions. Well, let's start with half-life. Half-life is once again, it's something you hear a lot about with radioactive decay. And the reason why is because with radioactive decay, a lot of times these isotopes or these radioactive elements are decaying at such a slow rate that to express that rate is just this really, really long decimal. And so to avoid these small, tiny decimals, instead they express how the isotope is decaying just in the time it takes for it to reach half of its mass, which is what we consider half-life. So if I think about half-life in any situation, if you have some principal amount and we're modeling it as an exponential equation, principal times e to the RT, what's going to be true about my rate? If we're working with a decay function, my rate's going to be negative, okay, because I'm working with exponential decay. But if I want to calculate half-life, what I'm really calculating is how long, so I'm going to be solving for t, how long will it take for my principal value for me to reach half of my principal value, right? Half of what I started with. How long is it going to take me to end up with half of what I started with? Kind of similar to how we calculated doubling time in our previous video, right? That was the same question, except it was how long is it going to take for me to reach double what I started with? And that applied to growth functions. Well, take a look at this. If I solve this, my very first step would be to divide by p on both sides. And what am I left with? I'm left with 1/2 equals e to the negative RT. So just like with doubling time, the principal amount, the actual amount you start with, doesn't actually matter with your half-life. You can calculate half-life without actually having to know your principal amount. The only thing you need to know is your rate. Because from here on out, I can use the natural log, and I end up with my half-life, which is a t-value, is equal to the natural log of 1/2 over your rate. Okay, and once again, because this is exponential decay, that rate should be negative. That rate should be negative. So I'll put a negative there just to remind you that your rate should be negative. Okay, and that'll give you your half-life. Okay, so you'll have a few problems on the homework where it's like calculate the half-life of this certain value. And you're welcome to pause the video and work on those right now. So let's actually do an example of half-life. Like I said earlier, half-life does not depend on your principal amount at all. Well, if I come back up here to my starting equation that I had, okay, we already said that this is an exponential equation. And I can write that as n equals some starting amount, e to the negative 0.062t. Right? I can write that as an exponential decay function, where my rate is negative 0.062, and so that goes up there in my exponent with my t variable. Well, we talked about this in our last video. This does not tell me anything about the initial value. I still don't know the initial value at all. But I don't need to know the initial value. I don't need to know the principal amount in order to calculate half-life. So let's calculate half-life real quick. What would the half-life of this exponential function be? Well, it's just the natural log of 1/2 over my rate, which, because this is decay, my rate is negative. Okay? Well, I can plug that into a calculator, right? I can just calculate natural log of 1/2 divided by negative 0.062, and I get about 11.2. Okay. Now, depending on your situation, this half-life value is going to be some sort of time unit. If it's in years, that's going to be the number of years it takes. If it's in days, it's going to be the number of days it takes for your amount to reach half of what it started with. Okay. So this is years or days or hours, just depending on your context. Okay. Okay. The next application I want to talk about is present value, and I kind of explained present value a little bit just when I mentioned it up here, right? It's you can think of it as, what should I invest if I want to have a certain amount after a certain amount of years, but the actual definition is the value of a sum of money in the present. So the present value, that's where the word present value comes from. So if we're talking about right now, the value of a sum of money in the present in contrast to some future value it will have when it has been invested at compound interest. Okay. So it kind of flips the problem, where instead of you knowing your present value, what you have right now, and you're wondering how much am I going to have after a certain amount of years, it's the opposite. I want a certain amount of years, or this is what I know I'm going to have after a certain amount of years. How much is that worth right now? So how are we going to calculate that? Well, based off of how we understand present value, that means this is the value that I don't know. Usually with present value, this value is given, your rate is given, and the time is given. And so you're solving for that p-value. Well, that means it might be helpful for me to isolate p, to get p by itself. All that takes is for me to divide by e to the RT. Okay, that leaves me with p is equal to a, my amount that I'm going to have, divided by e to the RT. Now, whenever we have exponents in the denominator, recall that you can rewrite that just using negative exponents. So that's what I'm going to do, is I'm going to rewrite that as a e to the negative RT. And this is my present value formula. You can calculate your present value by just simply taking your actual amount that you're going to have and multiplying that by e to the negative RT. Notice how I now have a decay function because we're going backwards. Your rate should be negative when you calculate present value. Okay? And that's what makes it a decay function. So let's look at an example of this. Let's say an athlete signed a contract where in 6 years they stand to make their salary will be $12 million. Okay? That represents a future value, right? Because that salary won't happen until 6 years have passed. So that's what their salary will be in 6 years. Okay? If I invest my money at a rate of 6.1%, so 6.1% interest, what is the present value? Okay, well, since I'm solving for present value, I might as well use this form. I might as well use my present value formula. So P is what I'm solving for. My actual is this $12 million. That's what I know I'm going to be, or what I know the athlete's going to be making in 6 years. Okay. Well, then I have e to the negative. What's my rate in this case? My rate is my interest rate. So I'm going to convert that to a decimal, 0.061. That's my rate. Notice how it's now negative because I'm going to be working backwards. This is now a decay problem because I'm trying to solve for the present value. And then what's my time in this case? 6 years. And that's nice because now that I have it in my present value formula, I don't need to solve for anything. I can just plug this straight into my calculator and get a value out. And so when I do that, I get about 8,322,000. And if I round to the nearest dollar, I get about $34. Okay, so his salary in 6 years is worth about $8 million right now, because if he just got that right now and then invested it, that's what he would have in 6 years anyway. Okay, very nice. Let's look at another example. I think there's a problem just like this on the homework, so you're welcome to pause and try that out before we start the next one. The last example I want to talk about is cooling objects. I mentioned this is another way that we can use exponential decay, because if you pull out, if you pull out a pie out of the oven or put something hot outside, it'll slowly cool down, and you can model that using an exponential function. Well, it turns out we already have the law of how things cool off. It's actually called Newton's law. Boy, does he have a lot of laws of cooling. Okay, and this law of cooling is really just an equation. It can be summed up as an equation. Okay, and that equation is capital T of T. Capital T in this case represents temperature, your temperature. Okay, I'm not sure why I wrote that as a J. Lowercase t is time, how long it sits out. And I have this equation, A times E to the negative k t. Notice how my rate is negative. It's a decay function. This is going to be a decay function. Plus c. Okay, so I have a few more variables in here. A few more, well, not necessarily variables, but constants that, I need to actually understand what they mean. K, of course, is still just your rate, and you can think of this as your rate of cooling for this type of problem. Okay, how fast is it cooling? But what about A? What about C? What do these values actually represent? Well, it turns out that, of course, the rate, how fast your object cools down, depends on what the temperature is that surrounds it. Okay, and that's what C represents. So C represents your surrounding temperature. And it turns out I could actually stop right here if I wanted to, because you can actually solve for A in any problem that I give it to you. But A actually does mean something as well. Okay? If your object starts at a certain temperature, A is going to represent how much hotter your object is than the surrounding temperature, right? Your object's not going to cool down to a lower temperature than what it is surrounding, right? And so A ends up representing the difference between the object's starting temperature and the surrounding temperature. And mathematically, I can express that as A is equal to T of 0, right? The temperature after 0 minutes, right? Right when I put the object out, minus C. Your starting temperature is always going to be more than your surrounding temperature, right? Because the whole idea is your object is cooling off. Okay. So that's what A ends up equaling, but you can always solve for that just with any of the data that I give you. So let's say we have a hot tub. Let's look at an example of this. Let's say we have a hot tub that's outside and it stops working. Okay, the hot tub breaks. Of course, if the hot tub breaks, then there's nothing there actually heating the hot tub up, and it's slowly going to cool down. So let's see if we can use Newton's law of cooling to help me kind of figure out what's actually going on here. Okay, so we're going to go ahead and say, so we've got a hot tub that breaks. The surrounding temperature is 72 degrees. Beautiful day outside. Okay. What is that going to end up being in my equation? This is going to be my C value. Okay. The hot tub has one of those thermometers that just stick in it. And so, through over a certain amount of time, you collected some data to see what the temperatures were. Okay. When the hot tub broke, the temperature was 107 degrees. That's probably why it broke, because I think that's a little too hot. I would not recommend hot tubbing at 107 degrees. Okay. And then after 10 minutes, the temperature is 89 degrees. Okay? It's reading 89 degrees. So, can we use this information to solve for some things? Okay. So let's ask the question, how long until the hot tub reaches 80 degrees? I could also ask the question, what will the temperature be after 19 minutes? Okay. Well, if I want to answer these questions, I need to use Newton's law of cooling. So let's set up my equation as best as I can. Temperature of T equals, well, once again, I can solve for A, but as long as we understand what A is going to represent, I can go ahead and put it in right now. A is my difference between the starting temperature and the surrounding temperature. If my hot tub broke at 107 degrees and the surrounding temperature is 72 degrees, that difference is 35. Okay. So I have 35 e to the, well, interesting, I don't actually have a K value. That's unknown for me right now. I don't have my rate of cooling. But I do know the surrounding temperature. So this is what I have so far. In order for me to answer these two questions, I need to know what my rate of cooling is. How am I going to figure that out? I'm going to figure that out using this information. I have one more data point that I haven't used yet. After 10 minutes, the temperature is 89 degrees. What does that tell me? That tells me that if I plug in 10, I should get 89. Well, plugging in 10 means, right, I'm putting 10 in for my T value, and I get this equation, which I can then solve for. I can solve for this. Okay, I'll subtract 72, and that gives me 17 equals 35 e to the negative k times 10. Divide by 35, I get 17 over 35 equals e to the negative 10k. I just switched the order of the 10 and the k. I'll take the natural log of both sides. This gives me the natural log of 17 over 35 equals negative 10k. Then I'll divide by negative 10. And I get that k is equal to the natural log of 17 over 35 divided by negative 10. Plug that into my calculator, and I get k is approximately 0.07221. So my cooling rate is about 7%. It loses about 7% of its temperature every minute. Okay. So, with that, now that I've found my K, I now have a full formula here. 35 e to the negative 0.07221 t plus 72. And with that full formula, I can now answer these two questions. Let's start with the second one, actually, because this one's a little bit easier. What will the temperature be after 19 minutes? Where does that 19 go? That's a time value. So I'm going to just plug it in for t. Okay, all that's asking is what's t of 19? I get 35 e to the negative 0.07221 times 19 plus 72. Throw that into my calculator, and I get about 81 degrees. Interesting. So that's actually pretty close to 80 degrees. That means my answer to my second one is going to be pretty close to 19 minutes. Well, let's answer the second question. So that's the first question answered, which was actually my second question, but regardless. Now, if I look at my second question, how long until the hot tub reaches 80 degrees? Where does that 80 go? What am I solving for? In this case, I'm solving for T, and 80 is going to go in for my output. So to set this one up, I have 80 equals 35e to the negative 0.0722119 plus 72. And I can solve for this. I'll subtract 72. I get 8 equals 35e to the negative 0.0. Oh, sorry. Not 19 to the 19. This is just raised to the... Sorry. I don't know what my t value is, so that should still just be t. So negative 0.07221t. I'll divide by 35, take the natural log, right? So I get natural log of 8 over 35 equals negative 0.07221t. Remember, the natural log is to cancel out that e, and then I'll divide by negative 0.07221, and I get t is approximately 20.4. So it takes about 20.4 minutes for my temperature to get all the way down to 80 degrees. Okie doke. So those are the examples I wanted to show you. There's a few more types of examples on the homework that I'm excited for you guys to try out and figure out on your own. But if you have any questions, please let me know. Have a great day, guys.